So this is a video of about gravitational potential and field at a point due to a spherical shell. So we will be seeing three different cases here. We will start with potential for a point outside the cell. Then we'll go to on the cell, and then we'll go shell. Sorry, and then we'll go to inside the shell. So let us now start. So now we have to consider potential, gravitational potential due to a spherical shell. So when I say spherical shell, I think you can imagine it is a sphere. It is a hollow sphere. So that is what I call a spherical shell. So what we have is we have a point somewhere outside the shell. Okay. So the gravitational potential due to this shell should be found out on this point. So for that, now let me consider this shell, and let this shell have a radius A, and let us assume the distance from the center of the cell to this point. I'll call this point P, and let me assume this distance to be some R. Okay. So now redraw this line. So what I do is, now I will assume this spherical shell, when I cut it, we know it is made up of numerous rings, right? It is made up of numerous rings. So what I'm going to do is I'm going to take one particular ring, and I'm going to find out the potential due to that ring on this point. And then obviously, as we always do, we are going to integrate that potential, right? So let me consider some ring. Consider a ring at any point. I'm considering a ring here such that this these are the points I'm connecting the ring. So let me assume with respect to the center, if I'm drawing two lines here, with respect to the center, this makes an angle theta. And again, let me assume this makes an angle d theta. Is that clear? So let me consider these points as C and E. Okay. So I have drawn two lines which is connecting us to this ring from the center. This is the ring in consideration. So I have drawn two lines, and this first line, which is connecting to this part of the ring, makes an angle theta. And between these two, the angle is d theta. Now, let me take this chord length CE. So let us go one by one. When you consider this chord length CE is equal to this distance A, right? And what is this angle? D theta. So A into d theta. I will call this some equation 1. So we know this CE is equal to A into d theta. Now let us consider the triangle, this triangle. If I consider here, sorry, when I consider this triangle, I now need this length. Okay, I now need this length. This is the opposite side. So you obviously know sine theta is equal to opposite side. Let me call it, I'm sorry. Let me call it some EF, whatever. So opposite side is equal to EF by hypotenuse, which is equal to OE. So I need EF. So EF is equal to OE sine theta, or this is equal to, what is OE? OE is going to be A sine theta. What is EF here? EF is the radius of this particular ring. You have cut out a ring that will have a radius, right? So EF is the radius of this particular ring. So now for this ring, I need to find out the area. So the area of the ring is equal to circumference into thickness. Now we know circumference is equal to 2 pi r, where r is the radius. But here, what is the radius of the ring? The radius of the ring is a sine theta. So you will have area of the ring is circumference is 2 pi a sine theta into thickness. This is the thickness of the ring. This is the thickness of the ring. CE is the thickness of the ring, which you have already found out as a sine theta. So 2 pi a sine theta into a sine theta. So area of the ring can be given as 2 pi a square. Sorry, this is a d theta. I'm sorry. This is a d theta, right? Sorry, 2 pi a square sine theta into d theta. This will give you the area of the ring, right? Now let us go on to the next part. Having found out the area, let us go on to the next part. So I will call this equation 2. Now, having this distance as r, now let me consider this distance as x. Now, what is this distance? This x is the distance from this ring to the point of consideration. Okay. So again, let me repeat, this x is the distance from the ring to the point of consideration. So I need to find out the potential due to this ring at this point. So, okay. So now let me write potential due to the ring. Sorry. So generally potential is given by minus Gm by R. This is the general formula for potential, right? So here it's due to the small ring. So I consider this as dV is equal to minus Gm by, so here the distance is x. So you are going to write minus Gm divided by x. Okay. So what do I have here? I have minus Gm, but I do have an expression for area from which from I have to find out the mass from area. So we know given a surface like this, density is this mass per area. So density is generally given by mass by this area. So what do we have here? Rho is equal to m divided by, what is the area we have here? Sorry, area we have here is 2 pi a square sine theta d theta. So rho is equal to 2 pi a square sine theta d theta. So wherein I will have m is equal to 2 pi a square sine theta d theta into rho. So I have this as mass. So this is equation 2. Let me have this as equation 3. So substitute 3 into. So what do I have? I have dV is equal to minus G 2 pi a square sine theta d theta rho divided by x. So this is my dV. So now I have an expression. I have a here. I have x here. So let me try to reduce the number of unknowns. So let me try to express a in terms of sorry, x in terms of a. So for that, let me consider this triangle. So when I consider this particular triangle, I can give, using the law of cosines, I can give this EP square as equal to OE square plus OP square minus 2 OE into OP cos theta. Let me write that now. So from triangle OEP, from triangle OEP, so I will have EP square is equal to OE square plus OP square, OE square plus OP square minus 2 OE OP cos theta. Okay. So what is my EP square? EP square is x square. So EP square is x square is equal to what is OE square? OE square is a square, right? OE square is a square plus OP square. What is OP square? OP square is R square. A square plus R square minus 2. OE is A R cos theta. So let me write this again here. X square is equal to A square plus R square minus 2 A R cos theta. Let me differentiate this. So what will I get? 2x into dx is equal to A is a constant, R is a constant. So both these when differentiated evaluate to be 0. So I will have minus 2AR into minus sine theta into d theta. So 2x dx is equal to 2AR sine theta into d theta. My 2 and 2 will get cancelled. So what do you have here? X dx is equal to AR sine theta d theta, or you will have x is equal to AR sine theta d theta divided by dx. So let me call this equation. So let me call this equation 4. And let me call this equation 5. So let us continue here. Substitute 5 in 4. Okay. So what is our 4? dv is equal to minus g m. We have already substituted for m, which is 2 pi a square sine theta d theta rho. 2 pi a square sine theta d theta into rho, right? And divided by x. So what is our x? AR sine theta d theta. AR sine theta d theta divided by dx. So which means I can put the dx here. So I will have a, this gets cancelled, this gets cancelled, this gets cancelled, cancelled. So I am reducing the number of variables here. I am eliminating theta here and I am only having dx here. So what do I have here? I have dv is equal to minus g 2 pi a rho minus g 2 pi a rho divided by r into dx. So this dv is the potential at a point outside the shell due to this small ring. So what do we have to do? Yeah, obviously, now to find out the potential due to the entire, now this expression is the potential at a point outside the shell due to a ring. So to find out the potential due to the entire shell, what do we have to do? Obviously, we'll have to integrate. So which means I will integrate dv, which is equal to integrating this minus g 2 pi a rho by r into dx. Now, what are the limits? So, your limit for the entire shell is going to be, now from here to here, it is r, right? Sorry. So, which means you'll have to find out from this point to this point. Now, if you take this point, this is on the shell, from here to here, the total distance is r. But you need to start only from here to here. So, the lower limit is going to be this entire distance minus this distance. So, your lower limit is going to be r minus a. Let me repeat again how the lower limit is got. You need to find the potential at this point from this point to this point. From this point, which means this is the lower limit. Now, from here to here, we don't know this distance. This to this to this, we don't know the distance. But how can we find out? We know from here to here, the distance is r. We also know from here to here, the distance is a. So, r minus a will give you this lower limit. Similarly, the upper limit is going to be r plus a. Okay. So, the upper limit is going to be r plus a. So, how do we integrate this? Let me go to the next. So, you are going to get integrating v is equal to minus 2 pi g a rho, right? A into rho divided by r, integral r minus a r plus a dx. So you will get minus 2 pi a rho g by r x within limit r minus a to r plus a. So you will get here v is equal to minus 2 pi a rho g by r plus a minus r minus a. Am I right? Minus r, minus of minus a. So r plus a. So you're going to cancel r, and v is going to be minus 2 pi g a rho by r into 2a. A plus a, 2a. So what do we have here? What we have here? We have 2 into 2, 4 minus v is equal to minus 4 pi g rho a square divided by, now 4 pi a square. Let me rewrite this. Minus 4 pi a square into rho into g divided by r. 4 pi a square is the surface area of this shell. And what is rho? Rho is the density of the shell. So surface area into density will give you the mass. So you will get here, you can write here minus g, this entire thing evaluates to be m, minus gm by r is the potential. So we have found out the gravitational potential. Now the gravitational field is dv minus of dv by dr. So you are going to have minus d by dr of minus gm by r. So what are you going to have here? You're going to have here minus g, sorry, it's going to be gm by r square. This is going to be your gravitational field due to a point. Now let us see the gravitational potential at a point on the shell. So again, you have this on the shell is somewhere here. It can be anywhere here. So gravitational potential on a point on the cell. So you have V, we'll take the same expression, minus of 2 pi g a rho by r into dx. Where do we get this expression from? Here. 2 pi, we have here 2 pi g a rho into dx. That is where we got the expression from. So we are going to integrate this. What are the limits? Your point can be here, and you can be anywhere, and it can be here. I told you the radius of the ring is a. So which means the limit will start from minus a here, and it will go up to plus a here, which means you can say minus a to plus A. Or what can you say? You can say 0 to 2A. Okay, minus A to plus A, or you can say 0 to 2A. So V is equal to minus 2 pi G A rho by R to dx. So which means on integrating, what will you get? Minus 2 pi G A rho by R x between limits 0 to 2A. So what will you get here? Minus 2 pi G A rho by R into 2E. Am I right? So what will you get here again? Again, what you are getting here is minus 4 pi 2 into 2, 4, A into A square rho G by R. Again, 4 pi A square, 4 pi A square rho, what is that? That is the mass. So again, you are getting minus Gm by R as the gravitational potential. So if this is going to be the gravitational potential, this is going to be your gravitational field for a point on the shell. So what is the last one you will have to do? For a point inside the shell. So now for a point inside the shell, so now this has a radius A. Am I right? And so let me consider inside the shell. I have a point somewhere here. This is at a distance R. Again, you will have V is equal to 2 pi G A rho by R into dx. So, now if you take this point from, if you take this is the distance A, so which means this point will have an influence here everywhere up to this point. When this point has an influence here, how will you take the distance? The total distance A minus this R, right? The total distance A minus this R will give you this lower limit. So your lower limit is going to be A minus R, and your upper limit is going to be somewhere here. So which means the total A plus this distance R. Upper limit is going to be A plus R. So V is equal to minus 2 pi G A rho by R x between limits A minus R and upper limit is A plus R. So minus 2 pi G A rho divided by R. You are going to have A plus R minus A plus R. Am I right? Minus of minus R is going to become plus R. So A and A is going to get cancelled. Minus 2 pi G A rho by R into 2R. Am I right? Into 2R. So your R and R, they are going to get cancelled. Minus 4 pi A rho into G. Okay. So now mass. So you have V is equal to minus 4 pi A rho G. V is equal to minus 4 pi A rho into G. But we know mass is equal to 4 pi A square rho. Is it not? So you have here V is equal to minus G. So this is 4 pi A square into rho. Here one A is missing. So what will you write here? Mass minus Gm divided by A. So V is equal to minus Gm divided by A will be your potential due to a point inside the shell.